All right, so we're in section 4.5 now, and what we're doing here is curve sketching. Curve sketching is something you've been doing since Algebra 1, when you first learn how to take an equation in two variables, y equals some function of x usually, plot points in the plane, and then connect those points into a curve or a line or something of that nature. You don't really go that deep with it in Algebra 1. You spend most of your time graphing lines, if anything, in that class. Maybe a parabola here and there, but not very deep. And then, as you progress through other levels of math, Algebra 2, pre-calculus, trigonometry, things like that, you learn more and more about how to graph functions. And you acquire more and more tools to do that as well. You learn about parent functions, transformations. You learn with trigonometry, how sinusoidal functions can have their amplitude, phase shift, period, all of those things changed and affected by the equation that you're looking at. In this section, though, we're going to be considering even more than that, because calculus has opened the door for us to know even more about the graph of a function by analyzing the function itself, the algebraic form of that function. Now, I will go ahead and just say that, of course, you have graphing calculators. We have things like Desmos that'll graph just about any function for you. And so you might look at this and question, what's the point of learning this? What's the point of covering this? Who sketches graphs by hand? And interestingly enough, you'll actually find, if you continue on in your math education, engineering, whatever your major happens to be, there will come a time here or there where you actually may need to sketch something by hand, or at least understand the connection between a function and its graph in a number of different facets, I guess I should say. So what I'm going to do here is go through the first 2 pages of my notes here are directly copied and pasted from the book, because what it's doing is it's breaking down kind of in a step-by-step way what you should look at when trying to get a very detailed graph out of a function by hand. And a lot of this is review, and towards the end of this, we're going to see where the calculus comes into play. So let's suppose that we're looking to sketch the graph of some function y equals f of x by hand. There are a number of different characteristics that graph might have that we want to determine before we try and actually sketch that thing out. So the first thing, A, is the domain of the function. It's always helpful to start there. Look at what the domain of your function is and make a note of that. B, intercepts. We do this with functions starting, early on in algebra. We want to know what the x and the y intercepts of a particular function are. That's going to give us points that we can plot right away on the axes. Next up is symmetry. Now, in I think for most people starting about trigonometry or college algebra, pre-calculus, that's about the time you start talking about symmetry. And we typically talk about 2 different types of symmetry in those sorts of classes. We talk about even symmetry and odd symmetry. And we can define them this way. If f of negative x is equal to f of x for all x in the domain of your function, then what's happening there is you have something called even symmetry. And graphically what that looks like is symmetry about the y-axis. So an example of a function with even symmetry is the function y equals x squared. It's a parabola. Do this. That's got a vertex at the origin, opens upwards, and it has symmetry about the y-axis. We call that even symmetry. Okay, you spend a lot of time in college algebra and trigonometry talking about that, so we're not going to go through a detailed discussion of that here. Another example of an even function, though, is the cosine function. Cosine is even and it has symmetry about the y-axis as well. Another type of symmetry, odd symmetry, is defined this way. F of negative x is equal to negative f of x for all x in your domain. And we call this type of symmetry odd symmetry, or symmetry about the origin. And an example of an odd function is the function y equals x cubed, which I'm not drawing very well, but it looks kind of like this. Okay, yeah, I did that really bad actually. This should have symmetry, which my bad sketching skills did not very accurately indicate. But the way odd symmetry works is you think of it as like two reflections. If I take everything that's to the right of my y-axis and then I reflect it once across the x-axis and then again across the y-axis, it should give you everything to the left of that y-axis. So I can see that if I were to reflect this little branch of my cubic function down and then over, it would overlap with this if I had drawn it correctly. That's odd symmetry. Okay, let's abbreviate that. Now your book includes this in the under the heading of symmetry. I don't know that I would really call it symmetry because it's very different from the other two types, but it's periodicity. This is talking about functions that have periodic behavior. Your trigonometric functions, all 6 of them are periodic, and all transformations of those functions are periodic, all the basic transformations. We can define a periodic function in a general sense this way. If f of x plus p equals f of x for all x in your domain, and p is some positive constant, then we say that this is a periodic function. So basically the idea is that if you pick any number in the domain of your function, and then you add p to that, plugging each of these into your function gives you the same output, the same y coordinate. And the same thing would happen if I went here, pick this point, whatever this is, call it b maybe, plug that into my function, get this, then do b plus p, I'd get the same output no matter where I did that. So that's like the general definition for what a period is. This number p here, that's the general definition of a periodic function. This number p here, if it's the smallest possible value for which this is true, we call that the period of that function. So the sine function, for example, has the property that sine of x plus 2 pi is equal to sine of x for all x in d. So the period of sine is 2 pi. 2 pi is the smallest number for which that's true. I could actually say that sine of x plus 4 pi is equal to sine of x for all x. That's also true, but 2 pi is the smallest positive number that I could put here for the sine function. That would work. So that's what makes that my period. We're not going to be looking at any examples of periodic functions in this lecture. I think I have one in the homework that I want you to do, but I'm talking about it here just for the sake of completeness. For a periodic function, when you're graphing one of those, the key there is to determine all of the characteristics of the graph to be able to basically just sketch one full period of that graph, because then everything else is just going to look like a copy paste of that. So you really just need to focus your attention on this one little period here and then copy and paste it. So that's 3 major points: domain, intercepts, and symmetry. And then we have more to look at. So next up is asymptotes, and we know that those come in 2 varieties. They actually come in more than 2 varieties, which we'll talk about in a moment, but horizontal asymptotes and vertical asymptotes. And we've talked about both of those in this class in the context of limits. Remember, horizontal asymptotes are what happens to a function when you take the limit as x approaches either infinity or negative infinity. You want to look at both, really. If that approaches a finite number, L, then that will result in a horizontal asymptote. So you need to include that in your graph. Vertical asymptotes look at limits as x approaches some finite number, either from the right or from the left. So we usually think of we use one-sided limits here because vertical asymptotes can affect a graph in different ways on either side of that asymptote. You can be approaching infinity on one side, but negative infinity on the other, for example. So we look at limits of these types, and those vertical asymptotes will only ever occur at places where the function's not defined. Actually, I shouldn't say that. I can come up with a counterexample where that's not true, but in general, or in most examples, that's going to be the case. So when you're searching for vertical asymptotes, a good place to start is points of discontinuity, where you might expect an asymptote to occur. And then there's another type of asymptote that we're going to talk about in this section called a slant asymptote. And we're going to hold off on discussing these until we get to the very last example. So we're just putting that there for reference for now. Okay, starting with E, we're starting to get into the stuff now where calculus is going to be used. So when graphing a function, we want to know what the intervals of increase and decrease are. And for that, we use the increasing decreasing test. Remember, that means you're looking at where your function is, or the derivative of your function is positive or negative. That's going to tell you where it's increasing, decreasing. You'll also want to look at where the first derivative has, or where your function has critical numbers, which oftentimes will occur when f prime of x equals 0. That's taking us to part F here. So looking for local maximum and minimum values. Remember, the idea there is to find critical numbers, places where your derivative either is equal to 0 or doesn't exist at all, and then determine using either your first or second derivative test if those are maximum or minimums when you find that. Maxima or minima, that's the correct plural. Okay. G, this is where we get into using the second derivative. We look at concavity and points of inflection. Remember, we have this thing called the concavity test, which we've talked about earlier in this chapter. The concavity test takes a look at your second derivative, and wherever your second derivative is positive, your function will be concave up. Negative, it's going to be concave down. If it's equal to 0 and concavity changes as you pass through that value, either from concave down to concave up or concave up to concave down, we call that a point of inflection. So knowing where those occur, those points of inflection, are useful in sketching our graph. And then finally, part H just says sketch the curve. Use all of the information that you found in those first 7 little categories to sketch the graph to the best of your artistic ability, which for me is not very, very good most of the time. Okay, so at this point, it's really just a matter of plugging away at some examples. And we want to, if you look at the homework will start out with some I think I assigned some of these anyways. The homework starts out with some pretty simple polynomials. I'm not going to do any polynomials in the lecture just because you spend enough time graphing those in college algebra and pre-cal. It's not really worth our time to look at those again. So I want to sketch this function, y equals 1 plus 2 over x plus 1 over x squared. And so what I want to do is I'm probably going to go back and forth between these first 2 pages and each example just to remind myself of what we're looking for. Start with the domain. Okay, what is the domain of this function? Well, this one's pretty simple to see what the domain is. You really want to look at where the function's not defined. It's not defined at 0 because I'd be dividing by 0 in either of these denominators here. So I could write my domain as this: negative infinity to 0, open interval, union 0 to infinity. In other words, it's the set of all real numbers except for 0. So that was pretty easy. Let's look at intercepts now. How do you find x-intercepts? To find an x-intercept, let's say x-intercepts, we're going to do that first. What you do is you set y equal to 0, and then you solve for x. So that would mean I'm looking at 0 equals 1 plus 2 over x plus 1 over x squared. Now what I'm going to do is multiply both sides of this by my least common denominator on this side, which is x squared. So that's still going to be a 0 there, equals x squared plus, this would become 2x, and this would just become 1, okay? But this is the same thing as x plus 1 squared. So this actually only has one real solution, x equals -1. So I'm going to have an x-intercept at -1, 0. Right away I know one of the points that I can plot on my graph. How do I find a y-intercept? Well, in order to find a y-intercept, I kind of do the opposite. I'd plug a 0 in for x. But as we already said, and when we looked at our domain, this function is not defined at 0, so there are no y-intercepts. Not applicable, or I could write none or something like that. Okay? So that's 2 categories down. Next thing we would look at is symmetry, but I'm going to leave it to you to check this. This function has neither type of symmetry. Right now we're not looking at well, I say neither. It talks about periodic functions, but I kind of mentioned before, none of the functions we're going to look at in this lecture are going to be periodic. So really, we're just looking at even and odd. It's fairly straightforward to plug in negative x into this function and then see that you don't get the original function back and you don't get the opposite of that function back. That's how you would check for those two things. So this one doesn't have either type of symmetry, so I'm not going to write anything for that. Okay, that takes care of our first page. Second page, I want to look at horizontal and vertical asymptotes. So starting with horizontal asymptotes, I don't want to mix my pages up. Let's do this. Asymptotes. Horizontal. So remember, what we're doing is we're looking at the limit as x approaches either infinity or negative infinity here. The limit as x approaches infinity of our function 1 plus 2 over x plus 1 over x squared. Remember, when you have these little reciprocal functions, or actually it's not a reciprocal function, but a function of the form a constant over x to a power, where that power is greater than 1, the limit as x goes to infinity will always send these to 0. You have a denominator that's getting really, really big and a numerator that's not changing, so it shrinks them down to 0, which means this is equal to 1. But notice the exact same thing would actually happen if I took x to negative infinity as well. These still shrink to 0. So regardless of which direction I'm going, we appear to have a horizontal asymptote at y equals 1. Okay? What about vertical asymptotes? For the vertical asymptotes, remember, we're not approaching infinity or negative infinity. We're approaching finite numbers to determine if the function has a vertical asymptote there. And as I said before, you want to look for where your function has discontinuities. In other words, is not defined in this case, to see if that's occurring. So this function is not defined at 0. I'm suspecting it might have a vertical asymptote there. So let's start by taking a look at the limit as x approaches 0. Let's go first from the right of our function. 1 plus 2 over x plus 1 over x squared. Okay, what's happening here? As written, it's a little tricky because I have two different rational expressions that I'm dealing with. So in a case like this, it's actually better to rewrite this whole thing as a single rational expression. This is the same thing as the limit as x approaches 0 from the positive side. If I got a common denominator of x squared, then combined everything, I would get x squared plus 2x plus 1 over x squared. Okay? Now, think about what's happening here. So I could either evaluate this limit directly, or actually, no, let me back that up. I don't want to evaluate this directly. What I want to do is think about the behavior of this function as x gets really, really close to 0. So if you were to plug in numbers that are getting closer and closer to 0, we're going to see that the denominator is positive. And let's look at our numerator again. Remember, we had this when we factored it, x plus 1 squared over x squared. I can't forget to write my limit in there. Okay, because my numerator and denominator are both squared, regardless of what positive number I'm plugging in for these, squaring them is going to guarantee that they also come out positive. So this is going to come out to positive infinity. We already know it's going to either positive or negative infinity, but that's narrows it down. Same thing is going to happen this direction as well. If I approach from the left, let's just go ahead and use the factored form of our function. X plus 1 squared over x squared. Again, I'm plugging in negative numbers because they're to the left of 0, but very, very close to 0. But regardless of the fact that they're negative, because I'm squaring my numerator and denominator, they're going to come out as a positive over positive again, so I get positive infinity there. Okay, so that describes what's happening at that vertical asymptote. Next up, what we want to do is look at intervals of increase or decrease. So now we're getting into the calculus part of things. I'm just going to call that ID. Okay, so in order to do that, I need a first derivative. The first derivative of our function, y prime, is equal to negative 2 over x squared minus 2 over x cubed. Okay, that's easy enough to verify. I'm going to let you do the derivative. It's just the power rule. And what we're doing here is we want to figure out where this derivative is positive and where it's negative. And as usual, we're going to start by setting it equal to 0 and then solving for that. So what we're going to do here is, again, multiply by the least common denominator, which is x cubed on both sides. And in fact, let's multiply by negative x cubed because we can eliminate these minuses here. If I did that, I'm going to get 2x plus 2 equals 0 here, which gives me x equals negative 1. Now, I'm going to create my little number line. X equals negative 1 is the only place where this was equal to 0. Normally, I'd want to check all my critical numbers. This is actually my only critical number. Remember, other critical numbers can occur where a function is defined, but its derivative is not. So it's tempting to look at this and say, well, the derivative is not defined at 0, so isn't 0 a critical number? And the answer is no, because the original function is also not defined at 0. This would need to be defined at 0, while this one is not, to consider it that type of a number a critical number. So negative 1 is our only critical number, and that means that we want to pick test points on either side of negative 1 to see what's going on with that function. Actually, I'm going to take back what I just said. I do want to include 0 here. Even though it's not a critical number, it's a point of discontinuity, and more specifically, it's there's an asymptote that occurs there. So what I want to do is, when you look at a vertical asymptote, you can change from increasing to decreasing as you pass through a vertical asymptote, or vice versa. So we actually do need to consider that. I take back what I said before. So this splits the number line up into 3 subintervals. You want to pick a test point on each one of these and plug them into your derivative. So for example, you could plug in, say, like negative 10 over on this side. Plug it into your function and see what's happening. In our case, you would see, you have to plug it into this guy right here. You would see that you would end up with a negative derivative. So f prime is negative here. Okay? Then you would want to pick a test point between negative 1 and 0. And I'm skipping the process of plugging numbers into this. This whole process takes enough time as it is. So I'm going to let you plug those test points into a calculator, see that you're getting the same results as I am. But here, if you plug in, say, negative 1/2 into this, you're going to find that your derivative comes out positive there. Okay, so we're increasing there. Then if you plug in something to the right of 0, so let's just pick 1. That one we can actually check pretty easily. If you plug a 1 in, I get negative 2 minus 2, which is negative 4. Clearly it's negative. F prime of x is negative there. Okay, so that's our increasing decreasing test. Next up, we want to look, if I go back to here, local maximum and minimum values. Okay, local max min. Now remember, local maximum and minimum values can only occur at critical numbers. And even though up here we said that we put these 2 numbers on our number line, remember we stated that negative 1 is the only one of those that's actually a critical number, because here is where an asymptote is occurring. So I would need to use either my first or second derivative test. It makes the most sense to use the first derivative test because we've already done the work right here. So this is a critical number, negative 1, and we know that our function is decreasing because its derivative is negative here. Oh, you know what, I actually just realized I didn't write out the intervals. I wanted to do that. Increasing on which interval? It's increasing on negative 1, 0, and it's decreasing on these intervals, negative infinity to negative 1, and 0 to infinity. Okay, so back to this. Local maximum, minimum values. If we're decreasing here, but increasing here, that implies that I have a minimum value. So I have a minimum of, now x equals negative 1 is not the minimum, right? That's just where the minimum occurs. So to figure out what the actual minimum value is, I need to take that negative 1 and plug it into the original function. So what would that be? 1 plus 2 over negative 1, so that's minus 2. 1 minus 2 is negative 1. And then if I plug negative 1 in here, I get plus 1 over 1, or just 1. Negative 1 plus positive 1 is 0. So that minimum value is 0. Minimum of 0 at x equals negative 1. Now, interestingly enough, that this would be a point on the graph, right? It'd be the point 0, negative 1, 0. But we have already seen that that function is also our x-intercept, because again, it's where y is equal to 0. So we'll see what the implication of that is once we get to the actual graph itself. All right, we've dealt with local max, local min. The only thing left now is to deal with concavity and points of inflection. So let's look at that. Concavity and points of inflection. Here we need our second derivative. So I'm going to take another derivative of my function, y double prime, and what I'm going to get, again from the power rule, is 4 over x cubed plus 6 over x to the 4th. And to find points of inflection, which you want to do first, we set this equal to 0. Remember, multiply by the least common denominator on both sides, which is x to the 4th. That would give you 4x plus 6 equals 0, so that x is equal to negative 3/2 when I solve that. Now, does that mean that we have a point of inflection at x equals negative 3/2? Potentially, but it's not a guarantee yet. We have to check, because this is the potential point where our concavity can change from concave up to concave down or vice versa, but it might not do that. So to see what's actually happening, we once again go to our number line and put that number, negative 3/2. Okay? So pick a number to the left of negative 3/2, say negative 10 or something, plug it into your second derivative to see what's happening. And if you do that, you're going to see that it is negative. F double prime of x is negative here. Again, you can do the arithmetic or the calculator work to verify that. If you plug in a number to the right of negative 3/2, let's just, and once again, sorry, like before, I also want to include 0 here, not because it's a potential point of inflection, but because it's a discontinuity, and specifically it's a vertical asymptote, and concavity can change across a vertical asymptote, so we have to make sure to include that. Pick like maybe negative 1, for example, plug that in here. You're going to get negative 4 plus 6, which is positive 2, so we end up with a positive second derivative there. And then pick anything to the right of 0, any positive number. If you plug any positive number in for my x's here, then this is guaranteed to be a positive plus a positive, which is positive. Notice I don't have a change in concavity there. I'm just concave up on either side of 0. So now we've put all this stuff down on paper, and the goal now is to turn this into a graph. Okay? So let's take this little bit of space that we have left down here to sketch a graph. So my domain is the set of all real numbers except for 0, and we also determined that 0 is going to be a vertical asymptote, x equals 0. So I'm expecting my y-axis to be a vertical asymptote here. Okay? Next up, what else do we know? We have an x-intercept, only one x-intercept, but no y-intercepts. So I know at negative 1, I'm going to have a point there, okay? That's that one x-intercept. What else do we know? Well, we know a little bit about the asymptotes. I mentioned the vertical asymptote already. The horizontal asymptote, there's one that occurs at y equals 1. So I need to make sure and include that in my graph. Okay? Now that we've done that, let's take a look at the increasing decreasing test. So we know that to the left of -1, our function is decreasing, and then to the right, it's increasing. In addition to that, we also determined that a local minimum of 0 occurs at -1. In other words, the point that we've already plotted is a local minimum. So our function is going to be doing something like that right there. Okay, notice how we're decreasing and then hit the critical number, or hit that local minimum, increase away from it, which is what this is telling us should happen. Okay, and then we also know that we are decreasing to the right of 0. Now, before I go and sketch stuff, I'm gonna do this. I'm gonna put a little arrow saying that I'm decreasing. Notice I put my arrow up here. I know that this is a vertical asymptote, so I know that we're going to infinity as I approach 0 from the positive side. So my graph's going to do something like this. In addition to that, look at this. To the right of 0, our function is concave up. So the fact that it's decreasing, concave up, that I have a vertical asymptote here and a horizontal asymptote there, pretty much tells me all I need to know to sketch this part of the graph. It's got to look something like this. Notice that satisfies all of that criteria. Concave up, decreasing the whole time, and approaching infinity as we approach 0 from the positive side. I haven't really dealt with this side yet, so I need to know what's going on here. I just have a little bit going on there so far. All right, so from -1 to 0, we know that our function is increasing because the derivative is positive there. Okay. In addition to that, we know that we are going to be approaching infinity as this approaches 0 from the left. So I'm expecting this to kind of go up and do something similar to this, but more of a mirror image of it. Or not a mirror image, but it's just approaching from the right or from the left. The second derivative is positive all throughout this interval as well, which is indicated right here. So what that's telling me is that we're also concave up. Concave up, increasing, approaching a vertical asymptote. This guy has to be doing something like this. Okay? What other information do I have? Well, to the left of -1, our function is decreasing. So I have this thing here. So I know that, everything to the left has to be decreasing towards that point. But how can I say more than just that? Well, I know that I have a point of inflection at -3/2. Now let's actually, I didn't write it down. Let's actually write down what that point of inflection is. Point of inflection is occurring at where x is equal to -3/2. And what I need to do is plug -3/2 into here to get the y coordinate of that point. I didn't do that ahead of time. I'm going to do that really quick. So, okay, so that comes out to 1/9 when we do that. So I have a point of inflection at -3/2, 1/9. So 1/9 is going to be, it's a little exaggerated here. It's not exactly accurate, but it's going to be somewhere around there. And let's say that -3/2 would be around here. Okay, so I have to have a point on my curve there. So I'm already not, I made this guy a little bit too steep. I just realized I was off camera there. So I need this guy to be concave up until it hits that point of inflection. So I'm going to ignore that part. And then it needs to switch to concave down there. But it still needs to be decreasing that whole time. So it's going to do something kind of like this. Switches to concave up at that point of inflection. And then that would be the rest of my graph, really. Although I just realized I ignored something rather important, didn't I? We still have this horizontal asymptote. So I need to correct myself. It's got to do something more like that. It's got to approach that horizontal asymptote. So I butchered this pretty bad, but that's what happens when I graph things by hand. The important thing, though, is this information up here. Getting this all correct. Okay, your artistic skills don't need to be on point. Let's go ahead and stop this one here.